Hi ladies and gentlemen, so today we're going to take a look at 6.6, inverses of functions. Our goals for the day are to determine if a graph has an inverse by using the horizontal line test, and to prove two functions are inverses using our knowledge of composition like we learned about yesterday. So let's first review what it means to find an inverse in the warm-up problem. I am going to move this down low so you can see the problem. Okay, so if f of x equals 4x minus 8, we want to find its inverse. Remember, f of x is the same thing as saying y equals. And the process of finding inverse is to take the x variable and the y variable and flip them around, then resolve this new equation for y, and that will result in the inverse function. So we're going to have x equals 4y minus 8. Solving this for y, using a little bit of our Algebra 1 skills, we're going to add 8 to both sides to get x plus 8 equals 4y, and divide by 4, and that's going to give us x plus 8 over 4. But remember, we should always use inverse notation. So f inverse, that what looks like an exponent of a negative 1, stands for the word inverse, equals x plus 8 over 4. If you wanted to simplify this to 1/4 x plus 2, that would be equally correct, but you do not have to do that. You can leave it as the fraction. The last thing on the warm-up says, what is the vertical line test? So remember, the vertical line test is what determines if the picture of a graph is representing a function. So for example, if I have this picture here, a parabola, and I start drawing vertical lines through my parabola, if it only ever crosses one point in my function, then that means the picture of this graph represents a function. If it crosses more than one point, like in this picture I'm going to draw, like here, it's crossing more than one point, so my second image would not represent a function, but the first one does, because the first one only crosses one point on the picture of the graph. So the horizontal line test is just the inverse of that, really. So what it means is when a horizontal line crosses the graph only once, the inverse of that picture is a function. If it crosses more than once, then that means the inverse of that picture is not a function. So if we take a look at example 1, is the following image a function? And then is its inverse a function? So to determine if the following picture is a function, we use the vertical line test. To determine if the inverse is a function, we use the horizontal line test. So the first one, if I draw vertical lines through this graph, I only ever cross one part of the graph at a time, so we can confidently say that yes, this image is a function. When answering the question, is its inverse a function? If I draw horizontal lines through this graph, I only cross one part of the graph at a time, so I can say yes, its inverse is a function. Example 2, is the following a function, and is its inverse a function? Pause the video, try this one on your own, then press play to see the answer. We can say that this one is not a picture of a function, so no, because when I draw a vertical line through this, it's crossing at more than one point of the graph on that vertical line. But if I were to draw horizontal lines, I could say yes, its inverse is a function because the horizontal lines only cross one point on the graph at a time. Example 3, same set of directions, is the following a function and is its inverse a function, but notice that our graph this time is just dots, it's not pieces that are connected. But the same process is going to be applied here. Is the following a function? So if I draw vertical lines through these dots, I only ever cross one dot at a time. So I can say yes, it is representing a function. Is the inverse a function, though? When I draw this horizontal line, I'm actually crossing two of the dots at a time, so I would say no, its inverse is not a function. What we're going to talk about next is finding inverses of functions that are not just linear, but of higher degreed powers. So find the inverse of f of x equals 2x minus 2 all to the power of 3 and determine if its inverse is a function, then state its domain and range. So first things first, to find the inverse, remember f of x is the same thing as y, so we're going to switch the y and x variables and then solve for y. So I'll have x equals, parentheses, 2y minus 2 to the power of 3. To get rid of this exponent of 3, because we cannot do anything that's inside the parentheses unless the exponent is gone, that means we need to use the inverse of raising something to a power of 3, and like we learned about in the last unit, that would mean we're taking the cubed root. So I have the cubed root of x equals 2y minus 2. Solving the rest of the way for y, I'm going to add 2 to both sides. So I will get the cubed root of x plus 2 equals 2y. Be careful because that plus 2 is not underneath the root sign, it's on the outside. And last, I divide by 2. And I end up with my inverse function, f inverse of x equals the cubed root of x plus 2 divided by 2. You don't have to worry about simplifying this. You can leave it as a fraction as is. When identifying the domain and range, this is really nice because our domain, we always just want to look, are there any restrictions or values we could not plug in for x? And when we're taking the cubed root, the nice thing about cubed roots is we can do that for positive and negative numbers. So our domain is going to be all real numbers. And with our domain being all real numbers, our range is also going to be all real numbers. Because if we were to graph this even visually, you can confirm that the picture of this graph is going to spread across the entire y-axis. It's going to continue getting higher on the positive y-axis and lower on the negative y-axis. The last part of this is to determine if the inverse is a function. So there's a couple of ways you could do that. You could, 1, graph the original equation and apply the horizontal line test. 2, you could graph the inverse function and apply the vertical line test. Either way, you'd be able to determine that yes, this inverse is a function. You could also think logically about it too, because if I plug any number in for x into this new equation, I'm always going to get a unique y value back out. So every input is going to give me exactly one output, which is the definition of a function.